you very much. So what I'll be doing today is I'll look back at the models that I've introduced yesterday, and I'll explain some properties and relations between the models. And I will also go a little bit deeper into what sort of models are reasonable for the real world. I'll also discuss some other models that have been investigated. All right, so this is what I did yesterday. I'm not going to go over this all again, but let's look at the conclusion from yesterday's talk. So there are many real-world networks from all sorts of different application areas. They share important features. Many of them are claimed to be scale-free in the sense that there's a huge amount of variability in nodal degrees across the network. Many of them are small worlds, meaning the distances in these networks are very small. And often in the applied world, there are suggestions that the degree structure is of infinite variance, so very heavy-tailed in terms of the probabilistic models. So we've described two models, the configuration model and generalized random graphs. And these models are chosen in such a way that they're very flexible in terms of their degree structure. So we're able to tune the parameters of the model in such a way that the degrees vary a lot. You have a lot of flexibility in choosing these degrees. Okay, let's see whether it does now show what I was planning it to show. Rather than, yes, this should be lecture 2. Rather than an empty page, small world phenomenon in random graphs. So we'll start a little bit by going back at the models. So this was the graph construction of the configuration model that I showed last time by doing a simulation. And the simulations are pretty convincing, but here's the description in words. So we think of all the vertices as having half edges connected to them, and you pair half edges one by one. And you do that uniformly at random. So a half edge is paired to a uniform other half edge that is out there. You may be worried about the precise order in which you perform the half edge pairings, but it turns out that this is an exchangeable process. So that means that these are exchangeable random variables, and it actually means that the order in which you do it doesn't matter. The result, at least in distribution, will always be the same. That's actually nice, and you can even do it on the fly, which is particularly useful if you want to do mathematical proofs. So what I mean here is that you can construct the graph as you go by pairing half edges one by one. For example, if you start from a vertex and then in a breadth-first way try to explore its neighborhood. Then actually it turns out that you're pairing the half edges in a random order, and also that is perfectly fine as long as you do it always in such a way that a new half edge that is unpaired is paired to a uniform half edge that hasn't been paired yet. Okay, so that's actually pretty nice. Now we do know that in such a model, it's very important to know something about what the precise structure of the degrees is. If the degrees are jumping around like crazy, you cannot expect that there will be some sort of a nice limiting behavior. So we've seen something very similar in the generalized random graph where the vertices have weights. Here, rather than having weights, we specify the degrees exactly. And we would like these degrees to somehow be sufficiently regular. And what this means is that the empirical distribution function, which is defined here, again is such that the random variable that has such a distribution function, in fact, that random variable is the degree of a uniformly chosen vertex, as you can easily see from here, that random variable converges in distribution to some limiting random variable. And then this limiting random variable really is the asymptotic degree distribution in your model. That's the way how you should think about it. And that actually is equivalent in this setting to the distribution converging for every value. And that's because we're dealing here with integer random variables. And if integer random variables converge in distribution to other integer random variables, that's equivalent to convergence of the probability mass function or the distribution function pointwise everywhere. Okay, so that's what we know. And then we also assume that the average degree, which is just this, also converges to the expected value of the limit. So there's no mass somehow running away that is substantial. This mean really is the mean of that random variable. And in some cases, and we'll see a bit later on when this is needed, we also need that the second moment converges. And in that case, we will assume that this second moment actually is finite. As we've seen, this is not always the case in real-world networks. In real-world networks, sometimes we have to think about this as growing with n. All right, so how can you choose your degree structure in an optimal way? Well, there are several ways how how to do it, I will generally assume that this condition is true, but if you wouldn't be able to find any examples for which this condition would be true, then we would be in a bit of trouble. And of course, there are standard ways how you can do it. You can, for example, take the degrees to be IID, and then all these conditions are just consequences of the law of large numbers. So that's something that you can do. The downside here is that there's going to be double randomness in your model. You have the randomness of the degrees, and then you have the randomness of the pairing of the half edges that actually constitutes the configuration model given the degrees. And that sometimes is a bit complicated. Sometimes it's easier to think about the degrees as being deterministic. And I'll also say a little bit more about why it's actually useful to set up the degree structure in this way exactly. That will also allow us to derive results pretty easily for some other models. All right, another thing that you could do is take some integer value distribution function and then again take this 1 minus f inverse of I over n. And again, this is a finite size approximation of, I mean, if you look at the distribution of this, of 1 minus f inverse of a uniform random variable, and again, this will have precisely distribution function f. So this is a completely deterministic, and in a certain sense, maybe a bit smoother approximation to the distribution function f. All right, and as I've been saying before, we will often be interested in power law degrees, and in this case, this tail distribution function decays like an inverse power of k, and if you then do this, it means that the degrees are growing like a power of n divided by j. So for a typical j, this is a bounded number, but if j is 1, this is a power of n. So that means that the largest degrees are really going to be very large, and they could have a pronounced effect in the network structure. That's what we would like to investigate. Okay? Now, as it turns out, for this configuration model, because it's so simple, it just arises by uniformly pairing all the half edges, it turns out that you can compute exactly what the limiting distribution of the graph is. In fact, for any n, and you have to be careful here because we've seen also in the simulations that there's nothing preventing us from having two edges between two vertices or a self-loop at a vertex. We're not making any of these restrictions saying that this is not allowed, so this could happen. So rather than producing a simple graph, what the configuration model typically does is it produces a multigraph. And that means that we have to describe it not just by an adjacency matrix, who's neighboring who, but in fact even by writing down how many edges there are between different vertices. So the xij's here are the number of edges between vertex I and vertex j. And of course, if you know all the xij's, you know exactly what the graph looks like. So this is a one-to-one mapping. And what you should bear in mind is that we also take these values xii, that in simple graphs would always be 0, but these are the number of self-loops at a vertex I, and this, in this case, can actually be strictly positive. And now, we start with a fixed number of half edges incident to every vertex, so that actually means that number is not going to be changing, and that actually means that there's restrictions on these xij's in the sense that if I perform this sum, then that should actually be precisely equal to di. And you should bear in mind here that the xii is counted twice, and that's because you eat up two half edges for every self-loop. Okay? So this is a restriction that will hold almost sure. So if I define ln to be the total degree, so the sum of all the degrees, that's twice the number of edges in my model, then you can compute for any such possible realization of the configuration model, what the probability is that the configuration model will actually produce that graph. And that's this very weird combinatorial expression. So this 1 over ln minus 1 double factorial, so the double factorial goes down by 2, ln is always even, it's a sum of degrees, that's the handshake lemma. So this is a factorial that goes down by 2 every time. And the way to think about this factor here is that this is the probability of any pairing. If I tell you exactly which half edge should be paired to which other half edge, that's what is called a pairing, sometimes called a configuration. That's actually the origin of the name configuration model, an invention by Barabasi. This actually is precisely the probability of any pairing. And the pairings are completely uniform, so every pairing has exactly the same probability. So this then corresponds, this nasty factor here, corresponds to the number of pairings that are such that you actually produce the same graph. So if I were to have two half-edges incident to a vertex, and I swap their pairs around, I actually get exactly the same graph. Okay? So you have to account for that. So that actually explains this factor here. If I sort of swap all the, permute all the half-edges incident to a vertex, I actually get exactly the same configuration, the same pairing. But you should be a little bit careful, because if I swap two half-edges that are incident, that are actually paired to one another, so a self-loop, then actually the configuration doesn't change. Okay, so that explains these factors 2 to the power xii. I'm overcounting the number of ways, and I have to adjust for that. And the same is true if you have multiple edges between different vertices. If I swap them around, then also nothing changes in the configuration. So that explains where this formula comes from. Now, of course, I mean, this is a nasty formula. I don't expect you to remember it, but I've put it up for a specific reason. And the specific reason is very simple. There's something very simplifying if I assume that my graph is simple. So if the graph is simple, that is if and only if the xii's are all 0 and the xij's are all 0 or 1. And in that case, this 2 to the power xii is actually 1, and actually the xij factorial will also be 1. Because 0 factorial is 1, 1 factorial is 1, and only when the xij's become larger than 1, you see these factors appearing. So what does this mean? This means that if I were to pick a j, a graph, such that all the xii's are 0 and all the xij's are in between 0 and 1, that's equivalent to being simple, my answer is always the same. Well, that's a very complicated way of saying that if I condition on simplicity, the result I get is totally uniform. That's actually quite nice, because remember that yesterday we were talking about how to produce a uniform graph with a given degree distribution. And I told you, well, it's actually difficult, and it's not even known how many you have. Okay, well, this is a way that will produce it. So if I run the configuration model, and I just accept the very first outcome that is simple, then that will be, in law, a totally uniform random graph with a given degree distribution. Now, in terms of Peter's talks, this is a simulation or a sampling strategy. If, of course, the probability of being simple would be vanishingly small, this would never work. So we'll return to that question, but this is certainly a sampling procedure. But turning that question around, it also means that you can actually compute what the number of simple graphs is just from this configuration model, namely the total number of graphs, simple graphs with a given degree distribution is this sort of trivial factor times the probability that the configuration model is simple. Okay? But this gives you a probabilistic answer to a deterministic question, namely how many are there? And it turns out, we'll see that later, that in many cases you can actually compute what this is asymptotically. Now this is a factor that you can actually compute for any choice, but this actually gives you an approximation formula for how many graphs you have with a given degree distribution. So this is one of the nicest examples, simplest examples of what is called the probabilistic method, namely you have a problem that is purely deterministic, namely how many simple graphs are there with a given degree structure, and you give an answer by actually translating it into a probabilistic question and answering the probabilistic question. This is the probabilistic method at its heart. All right. So yesterday I also discussed the generalized random graph, and I discussed several other models that are closely related to it. And here I will now explain why the generalized random graph is special. So in the generalized random graph, remember that the probability that there's an edge between I and j is this funny factor wi wj divided by ln plus wi wj, where the weights are given once and for all. This is the part where we're modeling something, and this ln is actually the sum of the weights. Now for this particular model, what we could do is condition on the degree sequence. Okay, that's a nasty conditioning, but we can do it. It's a discrete set of random variables. So that basically means what I mean here is that if I condition on the degrees of every vertex to be some specified value, di, whatever it is, 0, 1, 2, I do this for all of them simultaneously, then conditionally on this generalized random graph is actually a uniform graph over all graphs with that degree distribution. That's exactly what the configuration model was. That's a bit weird. Of course, here we're conditioning on a set of random variables, so the degrees themselves are random variables, but given these degrees, we actually know exactly what the distribution of the graph is. So in statistical terms, the degrees here are a sufficient statistic. Okay? Now what does this imply? Well, it implies, first of all, that if you condition on the degrees, this generalized random graph has exactly the same distribution as the configuration model when we condition the configuration model on being simple. So there's a very direct link between the two of them. Of course, the degrees here are random variables. Bear in mind that we were assuming things about the degrees in our configuration model. So if I can show that something like these assumptions would be true for the generalized random graph, and then I can prove sort of properties for the configuration model under such conditions, and also conditioning on simplicity, then these results will follow immediately also for the generalized random graph. So this has become sort of a nice route to proving results simultaneously for the configuration model as well as for the generalized random graph. If you pose the right conditions on the degrees, you can prove that these conditions are valid for the generalized random graph, then whatever result you're proving for the configuration model, if you can also prove it conditionally on simplicity, then you immediately get the results for free for the generalized random graph. So I will not be talking much about the generalized random graph after this anymore, because, you know, basically results tend to follow relatively easily from the configuration model. My guess would be yes, but I don't have it anywhere sort of immediately picked up. But my guess would be that you can derive a very similar formula such as this one in the bipartite setting. The proof is very simple, so I think you can just do it.
Not for the other result.
For the bipartite setting.
But I'm not talking about these results.
No, I mean the proof of this result is very simple. It's just one page.
The PIG is they completely analogous. Like now you have two ways.
Shall we take this offline? But yes, I mean, I have an answer to this.
Great.
You basically need weights on the left side and on the right side, and then you need to somehow
ln the right way.
You have to think about how to define the ln. Yeah.
Thanks.
Yeah. All right. Excellent question. Yes. Yeah. This is a very valid question. What is easier to prove in what setting? Generally, I would say that the generalized random graph is easier, and then this seems to be the hard way around. But this is not always the case. For example, if you were to be interested in the perspective from a random edge, even in the Ehlers-Danlos random graph, that's not so easy, because the edges are random, right? And so how do you properly define this? Well, this is a perspective that is very easy from the configuration model. Picking a random edge just means picking a random half edge and then another random half edge, because, you know, the pairing of those will be random. And then you get actually no information about anything else. So the perspective from a random edge is much easier in the configuration model than in the generalized random graph. I guess that, I mean, the theorem tells you how to do this. Take the degree distribution as it is in the generalized random graph, put that as an input in the configuration model as the degree distribution, and then condition that degree the configuration model on being simple. And you get exactly the same thing.
No, I was saying that it starts with the configuration model. I don't know
yes.
about what generalized random graph.
This is in general not possible. So the configuration model really is a lot more general. For example, in the configuration model, you could assume that the degrees are all one value, random regular graph. This is totally impossible in the generalized random graph. In the configuration model, you can assume that the degrees are all greater than or equal to 2. This is totally impossible in the generalized random graph. So you have much more flexibility in the configuration model in your degree distribution. Does that answer your question? Okay, thanks. Questions are always good. So I've been talking a lot about simplicity. And for simplicity, what we need to know is how many self-loops are there and how many multiple edges are there. There's a beautiful result that tells us how to compute the limiting distribution of the number of self-loops and the number of multi-edges. And it goes as follows. Assume that my conditions, the previous degree conditions are valid, and also that this second moment converges along as well. We will see why this is needed. Okay? Then if you look at the number of self-loops and the number of multiple edges jointly as a vector, then this converges in distribution to two independent Poisson random variables with two parameters, nu over 2 and nu squared over 4, where this nu is some ratio of expectations in which actually the second moment appears. Okay? So in general, if the second moment is finite, then these are finite values, and then it actually means that the total number of self-loops in the large graph limit converges to a finite random variable. And also the total number of multi-edges converges to a finite number. And that, in fact, even says that because the Poisson distribution has an atom at 0, it immediately tells you what the probability of simplicity is. Because then these two independent Poisson variables both have to be 0. So this has probability e to the power minus this times e to the power minus this. So if nu is finite, this is a strictly positive value. So you may be worried about the fact that, you know, in my huge configuration model, you're going to have a huge number of self-loops. This is not true, at least not under this condition. If you have a bounded second moment, actually the probability of simplicity will be strictly positive in the large graph limit. That's actually pretty nice. So that actually means that this sampling procedure of a uniform random graph, you can just compute the configuration model a couple number of times. You will have to do that a geometric number of times before you see a simple one, and you can stick to that. That's sometimes called the repeated configuration model. Yeah, that's a very good question. That's called the erased configuration model. It's a very legitimate question. You don't really get the right distribution, but it's almost the same. And this is, of course, I mean, when the second moment blows up, which is an important case, this is typically what we do. Then actually conditioning on simplicity is difficult. And actually the probability of simplicity is going to be stretched exponentially small. That typically sort of disallows you to do anything. And in that case, rather than studying a uniform graph with that degree sequence, we generally look at the erased configuration model. Or we just keep the multiple edges and self-loops. In many cases, they don't do very much. So how do you prove this? Well, it's Poisson convergence. You can use moment methods. Just compute all the factorial moments, show that they converged in the right way to the right limit, and then you're done. Yeah, so I mean, one measure of the mistake would be the number of edges that you remove.
But for example, some sort of like distribution on graphs, some Wasserstein distance.
Oh, they're probably in the large graph limit totally orthogonal. I mean, not here, but in the case where the second moment blows up, they are.
Yes, yes.
And the reason is very simple. You are going to be removing edges, so you can just look at the total number of edges that you keep and compare it to what it should be, which is deterministic.
Right. No, definitely there are going to be singular these two modes. But
yep.
If you look at the sum distance between graphs.
Yeah, so I'm saying that if you look at the total number of edges that you remove, that is a measure of difference.
Okay.
And you can show that that is small O of the total number of edges.
Okay.
So you're removing only a minor portion. Another way of looking at this is you could also say, you know, look from a vertex and what is the probability that you remove any edge in a K neighborhood? That will also vanish.
Okay.
So a typical point doesn't notice it. Does that answer the question?
Yeah.
Good. All right. So the third model that I was promising is the preferential attachment model. And this preferential attachment model is a dynamic model. And so it was proposed, and this was actually the onset of network science in a paper by Albert and Barabasi. I checked a few days ago. This one now has 34,000 citations. That's pretty amazing. It's a bit strange because actually the model they proposed was proposed, or very similar to it, by Yule in 1925 and by Simon again in 1955. And the simulation results that Albert and Barabasi were showing in their paper were actually proved by Yule and Simon in their papers. So this is something about sort of science being forgotten. This is a well-known thing. You know, people come up with beautiful models and then somehow 30 years later, somebody comes again and says, oh, you know, what is this model? And starts putting down conjectures that have long ago been proved already. This is quite interesting. So in preferential attachment models, the network is growing in time in such a way that new vertices are more likely to be connected to vertices that already have a high degree. That's why it's called preferential attachment. And this is sometimes called the rich get richer model. So people who are rich in terms of having many edges coming out of them, having a high degree, are more likely to get even higher degrees. But you know, if you think about it, it's actually the old get richer model, because it's only the old vertices that actually will have many edges. And in fact, the degrees of the old vertices will grow like a power of n. But if you look at a typical vertex, it will have a bounded degree. So the model is sparse. So what is the model exactly? And I'm not claiming the model or describing the model by Albert and Barabasi, but a slight generalization of it, which actually is important. So what we do is dynamically, at time n, a vertex comes in to the network. It has m possible edges to share to the older individuals, and it will choose every one of these edges, it will choose the endpoint according to a law that is proportional, to a probability that is proportional to the degree of the vertex to which you're attaching. If that degree is very high, then you're more likely to attach to that vertex. Now, of course, I'm saying this for one edge. You have to think about the joint distribution, and this is exactly what Albert and Barabasi didn't do. What you can do is you can do this in several ways. You can let the m edges attach independently, but you can also sort of update the degrees every time after which you attach the edges. That probabilistically is a slightly nicer model. And in fact, most of the results that you can prove in one model, you can also prove in another model. So I will be ignoring these kind of details. The important thing here is that, so this is a parameter. This parameter needs to be larger than minus m, because if it isn't, some of these numbers could be negative, and that's of course not allowed for a probability. You should normalize these, and that is something that you can do. So for any delta larger than minus m, this is a valid model. It's a dynamic model, and you can investigate the degree distribution in such a model. So this is a simulation. N is 1,000,000. We take m is equal to 2, delta is equal to 0, and that means that the power law distribution of the degree distribution, which we can rigorously analyze, is larger than 2. It's 3 in this case. And what you see in the degree distribution, so this is a simulation, you see, well, there's a straight line-ish effect somewhere here. Here it tapers off a little bit in the initial values, and then here again you see this sort of opening up a bit like in IID settings. But clearly these degrees are not IID. So this looks a lot like the degree distributions that we saw in our real-world networks, and what Barabasi claims is that this is the reason why you have all of these parallel degrees. So in the model by Albert and Barabasi, they didn't have this delta. The delta is important because you can look here at the slope, and that's the same thing as the power law exponent, and it turns out to be 3 plus delta over m. So by varying delta, you can actually change the power law exponent. And in many of the applications, we see power laws exponent that are different. It's not always 3. So it actually is worthwhile to have this sort of extra generality. Then you can also investigate what the role of, let's say, the power law exponent is. Okay? So this is what Barabasi says about it. Barabasi is not known as the most humblest person. He says, the scale-free topology is evidence of organizing principles acting at each stage of the network formation. No matter how large and complex a network becomes, as long as preferential attachment and growth are present, it will maintain its hub-dominated scale-free topology. Now, this is not exactly true as stated here. So you can come up with many models, and people have done this, where the preferential attachment mechanism is not affine. So here it's sort of linear in the degrees plus a constant. So I call this the affine preferential attachment model. But you could also take something else. For example, the square root of the degrees. That would still be preferential attachment, because it would still be the case that vertices with high degree are more likely to attract edges, but it will not have a power law degree distribution. So it really is the linearity or the affineness here that makes for parallel degree distributions. But it was a nice invention. It's a very simple microscopic rule that actually gives rise to networks that have degree distributions as we see them in the real world. And in the configuration model, you don't quite do this, right? You put in the degree distribution as an input. Here, it's actually being produced by the simple mechanism. And that's, in a certain sense, maybe more powerful. All right. Now, there's a lot of work on the degree structure in these networks, say a little bit about it. The very first proof was, again, for the delta is zero case by Bolobas, Riordan, Spencer, and Tousnadi. And Bolobas and Riordan also sort of rigorously define how the model should be defined. There are some issues in the paper by Albert and Barabasi, sort of, for example, how you get started in the model and these kind of things. So they've done that rather nicely. And then they have a beautiful proof for how you can investigate the number of vertices with degree k in such a model. So that's this nk of t. That's the number of vertices of degree k at time t. So if you want to look at the degree distribution, you should divide this nk of t by t, then you get the proportion of vertices that have degree k at time t. That's a random probability distribution. And they use martingale techniques in order to show that these proportions converge almost surely to a limiting probability distribution. And this limiting probability distribution is explicit. It's sort of a product of ratios of gamma functions. And if you perform asymptotics, for example, for very large k, then what you see is that this limit pk will, in the large k limit, decay as an inverse power of k. So it's approximated by a parallel. So typically these things come in two steps. What you can do is you can look at this martingale, so n is in between 0 and t, and you look at the conditional expectation of the number of vertices of degree k at time t, conditionally on the graph at time n. So this is a dupe martingale. If you take n is equal to 0, PA0 is nothing, so then you actually get the proper expectation. If you take n is equal to t, then PAT will give you all the information, so this is nk of t. And what you can show is that this martingale actually has bounded increments. They're bounded by 2m, almost surely. And that immediately says that, you know, if I want to compare m of t and m of 0, which is precisely nk of t minus its expectation, then that actually is very well concentrated. That is a zoom out thing. And that's the way how these things generally go. So we have very good concentration properties of this martingale, and therefore the random effects are vanishing. Of course, you still have to analyze how the mean behaves. And that you can do and show that the expected sort of proportion of vertices with degree k converges relatively quickly, even as t tends to infinity, to this pk. And there are many ways how that can be done. There's one in chapter 8, section 8.4, where we do this explicitly. Interestingly, when m is 1, you're creating a tree, and this tree can also be analyzed using continuous time branching process ideas. And Krishna Athreya has a series of papers on this. This is more difficult to extend to larger values of m, whereas this method is very general in m. But this is also a nice way of doing it. All right, how about more network models? Well, there's many more network models that have been invented because these very simple models that we're talking about generally don't have the properties that you would like to have. So for example, they have very little clustering, very few triangles, whereas social networks, for example, have many of them. So here are a few, let's say, fixes. You can add some clustering, basically, in the configuration model. Yeah?
So the preferential attachment model, when
Yeah.
it's grown for some time, the random graph model for suitable values of W, distribution of W, can they be made to be similar?
That's an excellent question. They're not going to be similar. And if you want to do the comparison, you should think more about the configuration model with the same asymptotic degree distribution. And they are similar and they're not similar. So we'll get back to that. So hang on to the question. So you can add clustering to the model, and then maybe it's a better model for social networks. You can also think about what happens when there's spaces being added, and the small world model is the most commonly studied model there. And the question is where this should be, useful. Somehow this model has entered into neuroscience, and all the neuroscientists are thinking about this as being the appropriate model to model the brain. I don't believe this, but okay, that's how it is. There is also something which is called the random intersection graph, and in the random intersection graph you're trying to model who belongs to which group. So for example, for the collaboration graph in MathSciNet or so, this might be an appropriate model because, you know, connections are being formed between authors because of papers they write jointly. Then, you know, when a paper is written between 5 authors, you add a complete graph between these 5 authors. And that's very similar to what the random intersection graph does. So application may be collaboration graphs. There's also spatial versions of many of the models that I've been talking about, so spatial preferential attachment models. All these random graph models discard space completely. And, you know, I would still guess that people who are sort of located close to each other are more likely to be connected than people who are very far apart. But closeness could mean many things. It could also mean that their jobs are related, right? I may actually be more likely connected to a probabilist who is in Bangalore, which is quite far away from Eindhoven, than to sort of a random individual in Eindhoven. So, you know, the distance could mean many things, but there are extensions to this in these spatial settings. There's one model that I would like to point out specifically. This is a model that's very closely related to the configuration model. We call it the hierarchical configuration model. The problem with the configuration model, as we'll see a bit later on, is that there's very few sort of short cycles. We've already seen that the number of self-loops converges to a Poisson random variable. The number of multiple edges converges to a Poisson random variable. And in a very similar way, you can also prove that the number of triangles converges to a Poisson random variable. A Poisson random variable is not very large, and what you tend to see in real-world networks is that the number of triangles grows linearly with the size of the network. So these models typically don't have that. This means that they're somehow locally tree-like. That's the term that has been phrased by the physicists. So rather than looking at the configuration model as being a description for, let's say, the individuals and their interconnections, what you could think about is having a model for communities and then having connections between the communities governed by the configuration model. And that's what the hierarchical configuration model does. So if you have some sort of a network with a community structure, such as here, what you see is that there's lots of small cycles, and this is generally not present in the configuration model. But what you could think of is this being collapsed to a single vertex, and then having the out edges be paired randomly amongst the communities. And that's what the hierarchical configuration model does. There's 2 versions. You could think of these small graphs as being fixed and given, and then only pairing the inter-community edges, or you could even think about sort of cutting up all of these edges also within the communities and pairing those according to a configuration model, and also pairing the edges between the communities in a configuration model. And the question is, does this look more like the real-world networks? So one way of doing that is by investigating what happens in such a model when you apply percolation to it. You could do all sorts of other things, but what you see generally is that these models, these HCM models perform way better than the original configuration model because they take the clustering in more detail into account. So for example, let's take this one here. This is one real-world network. I don't know which one it is, but what you see here is that if you perform percolation on the data, so this is really on the real-world network as it is, compared to these 2 sort of approximations to it, the curves are basically on top of each other. Whereas if you do it on the configuration model instead, you see that it's actually quite wide apart. Now, of course, here I'm using the fact that I know what the communities are. And the way how we did that was using community detection in order to figure out where the communities are. We were using the Louvain method. That's one of the claimed to be best methods to actually extract the community structure. So in a certain sense, if you look at this, one way of interpreting these results could be that, you know, the configuration model is a bad model for real-world networks, but at slightly higher level, it's a good model for, let's say, the connections between communities. The nice thing about this model is that it's still analytically tractable.
What's a good model in the community?
Yeah, so I mean, that's actually the funny thing, right? You would think that, you know, here you're actually maintaining many of the edges in your real-world network, whereas here you do it far fewer. But it turns out that these models are virtually indistinguishable. So this one level of hierarchy seems to be enough in order to describe these real-world networks, at least to a much better extent than the configuration model does instead. So we don't know what the insight is here, but what we just do is we basically draw a uniform random graph with precisely those degrees. And since these are relatively small, you can do this. So the insight structure is not that relevant. No. I mean, it's not even clear how to define the problem. So there's quite a bit of work on statistics of networks. For example, fitting of, let's say, preferential attachment functions on the basis of real-world data. But these problems tend to be quite hard, and people tend to look at relatively simple models because the statistical problems just become so hard. And goodness of fit I haven't seen. So we've been thinking about this a little bit in the context of citation networks, but it's hard. And, you know, in a certain sense, statistically speaking, this whole realm of network science is an area where all models are wrong. Right? This is a phrase from statistics. If you have sort of lots of data, you tend to be able to sort of see the difference between your model and the data, you know, even if this difference is extremely small. Right? So all models are wrong, but the models may still be useful. It's a bit similar to what Peter was talking about. You know, your model may be 5% off. But still the analysis of it is actually quite useful. But 5% statistically is huge. Okay? All right, so I would like to close by saying a little bit about some of the properties in these models. For example, the size of the giant component. What we tend to see in real-world networks is that they're highly connected. So if you inspect the largest connected component in your graph, either that's everything, that's actually quite well possible, or it's a large proportion, 90%, 80%, or something like that. This is, of course, in many cases not enforced. The internet is special in that respect. So the internet has to be connected. So there you know that the giant component is everything, by nature, by construction, so to speak. But this doesn't have to be. In a collaboration network, why should everybody be connected to everybody else? This is generally not the case. But generally, these models are what we would call supercritical in the sense that there is a giant component that is sizable. And there's been a lot of work in analyzing the largest connected component in the configuration model or in uniform random graphs with the same degree structure. And generally, you can find an explicit criterion that tells you when you have such a giant component. So what you see is that if you look at the largest connected component divide through by n, or the size of the largest connected component divide through by n, then this will converge in probability to some limit. And this limit is strictly positive precisely when a certain criterion holds. So this is nu is larger than 1, where nu is, again, this funny thing that we've already seen in the simplicity. And this should really be interpreted as being the average outgoing degree of a randomly chosen half-edge. And why that is relevant will come up later. This is related to branching processes. It's not a coincidence that we compare here to 1, right, which is the critical value for a branching process. So if my underlying branching process, which I'll have to explain how it arises later on, if that underlying branching process has a mean offspring that is strictly larger than 1, then there will be a giant component. And in fact, the way how you should interpret this is, if I were to pick a random individual and suppose that its neighborhood really looks like a branching process, then with a certain strictly positive probability, it will survive to, let's say, a very large number of generations. But if it does, then it should be in the giant component. So indeed, this number here can be interpreted as being the survival probability of an appropriate, let's say, local approximation of your graph. right? So it's also possible that this configuration model is actually completely connected. This is, again, not going to be true for the generalized random graph. This occurs with high probability when the minimum degree is at least 3, and it occurs with strictly positive probability when the minimum degree is at least 2. So when the minimum degree is at least 2, if I look at a vertex, I look at a half-edge incident to it, I pair it to another half-edge, then there is always at least one extra half-edge coming out of that vertex. That's what this says. Right? So that means that somehow, with high probability, your neighborhoods will keep on expanding, and you will never die out. All right? So for the generalized random graph, we can do very similar things. I will not spend a lot of time on this because we've already seen that this configuration model and the generalized random graph are very closely related. So this result can actually be seen to be following rather directly from the previous one. But I wanted to talk in a little bit more detail about small world properties. So if you think about the configuration model, what we're doing is we're putting in the exact degree structure. So the fact that the thing is scale-free, well, that's by construction true. So this model cannot explain, contrary to the preferential attachment model, which may offer a possible explanation for why you see these scale-free degree sequences coming up. But of course, the neighborhood structure, either the giant component or distances in this model, we don't say anything about that. So what you can now do is you can investigate precisely how these graph distances depend on the degree structure that is available in the network. And that's exactly what we're aiming to do. And remember that we were seeing in these small world networks, these real world networks, that generally distances are quite small. So the question is this being reproduced by the models that we've now phrased? So there's two settings, and this is not so strange. This is related to the branching process approximation again. What we do is we look at a random variable that describes the graph distance between two uniformly chosen vertices inside the graph. So again, there's double randomness, there's the randomness of the graph, but there's also the randomness of the choice of the vertices. Okay? So I'm deliberately not looking at the diameter here, because diameter is a sort of a not very robust thing. It can change rather dramatically by just changing a few edges, whereas these typical distances are much more robust. Okay? So there's two settings, again, a setting where the second moment is finite, and in that case, the graph distances grow logarithmically with a certain base that is exactly this number. So this says that the graph distance is roughly log n divided by log nu, and log nu, when nu is larger than 1, is strictly positive. So graph distances there grow logarithmically. And you should really think of this as being morally equivalent to neighborhoods growing exponentially. So if neighborhoods grow exponentially, then typical distances should grow logarithmically. Okay? Then there's a second regime where now we're assuming some form of a parallel degree distribution with a tau that's in between 2 and 3. For example, IID degrees or something like that. And we investigate the graph distances in the configuration model. And then it turns out that the graph distances grow doubly logarithmically. And with some specific constant, and this constant only depends on this precise choice of the parallel exponent. Okay? Now, logarithm already grows pretty slowly within, but log doesn't grow at all. I mean, if you do simulations, you really have to simulate very, very, very large values before you start seeing that log n actually grows. And that's sort of this picture. So here, the top picture here is log of x, where x is of the order of the population of the Earth. And you can see that it grows even though it grows slowly. This is log. From my standpoint, I can see that it does grow. So particularly here in the beginning, you see that there is a little bit like that. I can still see that it goes up a little bit, but for you, it looks like a constant. So this basically would predict that if let's say the population on Earth would grow by a factor 2, distances would not grow at all. This may be an explanation for why this 6 degrees of separation effect has been already claimed in the 20s or in the 30s. It hasn't really changed. right? So I see this as, let's say, a mathematical version of 6 degrees of separation. You do need that distances grow, but they grow so slowly that it's hardly visible in any numerics. That's what it says. Okay? I was already mentioning the diameter, and the diameter can also be studied. It's much harder, because somehow, for typical distances, you pick 2 vertices uniformly at random. So if you understand what the local neighborhoods of these random individuals look like, you can compute what graph distances are. For the diameter, you don't look at typical individuals, but at worst case individuals. So these are probably the individuals for which there's only very few vertices, even at a relatively large distance, which is highly unusual, but still possible, right? And then it turns out that the diameter is again logarithmic in many cases, with a first factor that is actually identical to the factor that we see here, but then there's some added little bit to it. And this added little bit is strictly positive precisely when you have a strictly positive probability when that the degree is less than or equal to 2. Okay? And this is understandable because if you have a positive proportion of vertices of degree 2, you could actually pair many of them together in a long string. And because the degree is 2, you're going to have a path. There's nothing else there. And actually the distance between the starting point and the end point of this very long path is actually going to be, again, logarithmic. Okay? Now imagine that you have this very long path, but now attached to a random individual. Then you're actually increasing your distances quite substantially. Now, it turns out that this is sort of if and only if, at least in the regime where tau is in between 2 and 3, and we'll stop very soon, when the degrees are at least 3. And then again, the distances turn out to be log-log. So you see a phase transition here depending on whether this number here is strictly positive or not. I'll say a little bit more about other models later on, but let's go to the conclusions and finish up. So we've seen many real networks that share important features. I've started with this, and there's often a suggestion of infinite variance degrees, and one of the things that we see is that these infinite variance degrees play a profound role in the network structure. In these infinite variance degree models, you tend to see distances that are ultra small, as they're called. Small is logarithmic, ultra small is smaller than that, and in this case it's even doubly logarithmic. So we've seen some models to explain or to model these networks. Configuration model, generalized random graph yesterday. We've discussed some properties of those, as well as preferential attachment today. And the nice thing about the preferential attachment model is that it can really help to explain why we see parallel degree structures by providing a very simple microscopic rule that will produce these degree structures. And I'll say that in more detail tomorrow. The distances in such networks are remarkably universal across the different models. But that I will explain in more detail tomorrow. Thank you very much.